So we're going to start by looking at the GMM estimation principle, which is the overall principle that guides the estimation of what I call the modern methods to estimate the spatial lag and spatial error model. Spatial lag case is very straightforward. That's instrumental variables. Spatial error model is a little more complicated because then we'll have actual moment equations to solve for. So I'm going to start with a general principle, the method of moments, and then its generalization. Method of moments is very old principle, and it's based on something that you've already seen, that the average of a sample in the limit converges to the population mean. I gave you the example of doing a simulation. If you simulate 10 standard normal variates, you take the average is not going to be 0. As you increase the sample size, you do 100, 1,000, 100,000 is going to get closer and closer to 0. So the sample mean, which is the average, approaches in the limit the population mean, the true parameter value. And that can be generalized to any kind of sample moment. So the mean is a sample moment, the first moment. The variance is a second moment, third moment, fourth moment. Any kind of moment computed from a sample, as long as your sample becomes large enough, converges to the population parameter of interest, the population moment of interest. Very old principle, law of large numbers, basically translated, Law of large numbers, it's the same thing. The population mean converges, the sample mean converges to the population mean. This principle gives us a way to set up what is called empirical moment conditions or empirical moment equations. In essence, they take the equality, even though it's in the limit, of the sample average and the population parameter and express that as something that's equal to 0. So the on average, and here again, we have the 1 over n, which can be applied to each of these. But of course, if you add up the mean, mu, n times, and divide it by n, you get the mean back. So this is immaterial. But the first term is the average of the y's. Set this to 0. If you solve this, so the trick is you come up with the proper moment equation, which sets the sample average, sample mean, equals to the population mean, which is typically a parameter of interest. You express that as something equal to 0, and then you solve it. So here we have our empirical moment condition for the mean. We solve it, which gives us that the methods of moments estimator of the mean is the average. What else would it be, right? Now, what do we do with this principle in a regression context? Same thing. The key is, what are the empirical moment conditions? Something that is an expression equal to 0 that contains the parameters of interest. Something that holds in the limit and will translate that to the actual sample. And for a regression, we can just go back to our basic assumptions, which stated that the explanatory variables are uncorrelated with the error term. We can write this as a conditional moment condition. This is technicality. In essence, it boils down to this thing at the bottom, that we have an expression that we know is true in the population. We're going to express it in the sample and solve it. Where's our parameter? X doesn't have a parameter, but U does. U is the error term, which is y minus x beta, and beta is the parameter of interest. To solve this, we take the average of the product of all the products of the X with the associated error term, which has the beta in it. OLS can thus be expressed as a methods of moments estimator. I mean, the first time you see this, you think, oh, what's going on here? But if you had OLS estimation the old way, I don't think they do teach it that way anymore. They actually mentioned moment equations. But at the time, they never said this is a methods of moment estimation. But the moment equations are simply these products, and they should be familiar. This is X. X is not random. This is the error term, which contains the unknown coefficients beta. We have our equations. We solve the equations. What's the solution to this system of equations? Because it's a system. It's the least squares estimator. Right? This is expressed with the summation of the individual terms. And at the bottom here is the familiar expression for least squares estimation, x prime x inverse, x prime y. So least squares is a methods of moments estimate. Two-stage least squares is a methods of moments estimate. Now again, what are the sample moments? What are these conditions that are equal to 0 expressed in the parameters? We replace them by the sample, we solve for the parameters, and we're in business. The condition is, this is where the instruments come in. Remember, the problem that instrumental variables addresses is endogeneity, simultaneous equation bias. So there are some right-hand side variables, some x's, that are actually correlated with the error term. So we can't use x prime u because some of this is not 0, so that doesn't work. But we can use the instruments because the requirement for the instruments is that they are not correlated with the error term. So now we have the same thing as before, but we have the instruments Q replacing X. And if X is truly exogenous, its instrument is X itself. If it's endogenous, remember, this is the 1-for-1 case, right? Two-stage least squares, we have more for 1. This is 1-for-1. And same thing as before, same expression, but here we have the instrumental variables estimator, Q prime X inverse Q prime Y. Remember, for this to work, Q has to have the same dimension as X, right? So this is the 1-for-1 case. If we have more instruments, then we use as the instrument, not the actual instruments, but the predicted value of a regression of the endogenous variable on the instruments, right? And still, once we have that predicted value, we're back in 1-for-1. So all these estimators can be shown to be methods of moments estimators. What is a generalized methods of moment? Well, so far, we always had as many equations, as many conditions as we had parameters. For OLS, we have K, 1 for each beta, and instrumental variables, we also have K, 1 for each beta. What if we have more equations, more conditions that hold than we have parameters? Okay. Since I don't want to spend too much time on this, there's a really great example of this in the Green Econometrics textbook. It's been in there for years. And it's the case of the gamma distribution. If you're not familiar with the gamma distribution, it has two main parameters. They're not the mean and the variance, but they're related to the mean and the variance. They're usually called alpha and beta, right? And you can set up 4 different moment equations for the 2 parameters. So in that case, what do? You could pick any 2 of the 4 and solve them, and you have methods of moments estimates for those parameters. But that's not optimal in the sense that it doesn't take advantage of all the information that you have. You have 4 equations. You only have 2 parameters. So each of these 4 equations has to be equal to 0. That's not possible. You can get 2 equal to 0, but then the 2 others are not equal to 0, right? 2 out of 4. A compromise, and this is always the same logic, is to get all of them as close as possible to 0, which is, again, least squares. We take the square deviation from 0 for all 4 and make it as small as possible. Okay. That's the idea behind the generalized methods of moments. Only it's not least squares, it's weighted least squares. Because each of these moment equations do not necessarily have the same importance. If they all have the same importance, we give them all the same weight. If they don't have all the same importance, we give the more important ones more weight than the less important ones. Okay, what's important mean? It means precision. If you think of heteroscedastic estimation, weighted least squares, what do you weigh by? By the inverse of the variance. So the observations, if the observations in heteroscedasticity, one way to interpret it, one way to translate that, is to say that the error term in each observation has a different precision. Like you get better estimates for low-income people than for high-income people, okay? So if you have all these equations, low-income people, high-income people, if the precision is greater for low-income people, you give them more weight to balance things out. So the weighted logic here, the way you think about it, is that you weigh inversely to the variance of the condition itself. Now, this all seems very abstract. Just think about it, that each of these conditions is a random variable because it's computed from the sample. So there's some randomness in it. Do we necessarily know the precision? Not necessarily. But we know that there is such a notion. You know, every random variable has a mean and a variance. Some don't have a variance, but that's excluded in our conditions. So if we knew what that variance was, we could weight them in an optimal way. If we don't know what the variance is, we still can weight them, but we know that we're going to get a good solution in the sense of a consistent estimate, but we don't know much about the quality of that solution in terms of its precision. Okay. What? Okay, I'm not there yet. So H is any moment equation. So any functional form. In our previous example, H was the product of X with the error term, right? And I write this like this because it's extremely general. The VI contains all the variables, including the error term. So this allows for very nonlinear type of estimations. And the theta is the parameter vector of interest. The key here, and the key differentiating characteristic, is that we have more equations than the dimension of theta. So what we do is we have to solve the system of equations for theta. You know, remember, I think this is algebra, I don't know anymore, but you have more equations than unknowns, okay? You have a problem. Because you can always, you know, pick some equations, but that doesn't necessarily satisfy the other ones. So rather than solving it, which we can't, we get the next best solution, which is get as close to 0 as possible in a least square sense. And that's what the GMM estimator is. It's this monster here, which is nothing but weighted by this W. You have L conditions, L equations, K unknowns. L is larger than K. So for each of these equations, we minimize the sum of squares of deviations from zero weighted by W. Okay. So a lot of unknowns here. What are the H's that we need to pick? Which conditions are good conditions? And what are the weights that we need to use? Okay. But in abstraction, it's a very simple principle. We have more equations than we have unknowns, so we're going to minimize this weighted sum of square deviations. Very simple. This is where it gets a little complicated, and I'm just showing this to you, so if you see this in articles, you're not thrown off and it looks familiar, but it gets kind of complicated. The major breakthrough is to show that this actually works, and it works in a well structured manner. And a well-structured manner is that we have asymptotic normality. So as we go to the limit, we get consistency, which means we will be getting the right values for the parameters from solving these equations. But we also get a nicely structured asymptotic variance matrix, which is this A inverse B, A inverse. The problem is that A and B are kind of complicated. A and B consist not only of these weights, which we don't know what to pick, but also of the partial derivatives of the moment conditions, partial derivatives with respect to the parameters. So for each of these moment conditions, you have them. You take the partial derivatives. That gives us this matrix G. With G and the weights, we get A and B. Okay. And if we knew the variance of the moment conditions, what would we set W to? So S is the variance of the moment conditions. We multiply S by the weights before and after. How do you get rid of S? In a matrix multiplication. You have a matrix A. You multiply by the inverse, right? So if we pick W as S inverse, this whole thing simplifies. Because we have S inverse, S, gone, S inverse. So instead of 3 matrices, we have 1, S inverse. The optimal set of weights is the inverse of the variance of the moment conditions. Now that's a mouthful. We don't know what that is, right? That depends on the moment conditions and the randomness that is part of the moment conditions. Where does that randomness come from? It comes from the error term. What do we assume about the error term? That will determine the variance of the moment conditions. So mathematically, it gets very complicated. On an, if you can call it an intuitive level, it's not. Whatever you assume for the error terms, IID, normal, not normal, constant variance, not constant variance, correlated, not correlated, that gives you enough structure to figure out what the variance of those conditions would be, because it's all in the U, in the error term. It's not in the X's, right? And whatever randomness is in the Y is directly a function of the randomness in the U. So there's nothing new added by this Y. So if we have what we call the data generating process, the DGP, which is whatever we assume about the error terms, we, in principle, if we're really good at math, can figure out what the variance is of these moment conditions, right? It's just basically mathematical statistics. So then we're in business, we have our optimal weights as the inverse of that variance, which depends on our assumptions, and the whole set of products simplifies the variance, the asymptotic variance of this GMM estimator simplifies. And of course, we need to estimate this inverse of the variance. But as it happens, we only need a consistent estimate. So as long as it's consistent, it doesn't really matter how efficient it is. That was also, if you recall, the case with instrumental variables. With instrumental variables, it doesn't really matter what instruments we pick to get consistency. The only thing we want is that the instruments are not correlated with the error term. But to get efficiency, to get better precision, it does matter which instruments we pick. Okay? It's kind of the same thing here. We don't worry about efficiency. We don't have to worry about it, which makes it easier because all we need to worry about is that we have consistency. That gives us an approach to implement this in practice, and we'll see this later today. It's basically a two-step or a multi-step estimator. The first step, we just want consistency. We don't care about efficiency. We know that the solution to these moment equations, no matter what the weights are, will give us a consistent estimator. So we get one. And the easiest weights matrix is an identity matrix, which is simple least squares. Second step, we have our consistent estimator. We plug that into the variance expression, and then we use the inverse of the variance matrix as the optimal weights in the second step. So first step, straight least squares. Second step, weighted least squares. And then we get our estimate and its variance. In a nutshell, that's what it is. It's, as I think on an intuitive level, it's actually not that complicated. Of course, the devil is in the details. You know, what are these assumptions that we make about the error term? How does that translate into variance expression? How do the parameter estimates plug in to these variance expressions, and so on? So the math typically in these derivations, if you look at the original papers, the appendix is all the proofs, and it's just, you know, very, very complicated. But at a basic level, it's actually not that complicated. Just do the straight least squares, get the parameter estimates, plug them in there, do the weighted least squares, and you're in business. And then all these properties of consistency, efficiency, and all that other stuff, you don't have to worry about it. Some statistician or some theoretical econometrician came up with the proofs, so we know it works.